Total internal reflection is important in technology. A lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates audio information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the material. So it works for glancing angles, and the beam needs to be confined within a material that is more optically dense, has a higher index of refraction than the surrounding material. But any shape will do. You can use a rectangular shape here, you can use a circular shape, confining all that light inside of that fiber. This is a more typical light optical cable or light fiber. I'm just going to introduce the beam here. You'll see it come out on the far end. This is an example of, we have a source of light in the base here, and each of these, all they are strands of plastic, and they are channeling the light through them. And they can be bent or whatever, and they'll still channel that light. There is a certain radius. If you bend it, if you kink it really hard, then that brings you away from the total internal reflection, and you lose the effect. But very effective, very important in today's technology, total internal reflection.
Welcome back to my channel. Today we continue chapter 6, Light and Optic, on topic 6.2, Total Internal Reflection, part 1. So you can see from the picture here, a reflected image of the turtle can be seen on the boundary of water and air. Okay, why does this happen? So this phenomenon is known as total internal reflection of light. Total internal reflection only occurs when light travels from a medium of high density to medium of low density. As you can see here, light travels from the object, that is the turtle, to the air, from water to air. Okay, so the image that forms at the boundary is due to the phenomenon of total internal reflection. So what is total internal reflection? We will discuss later the definition. Now you can refer to your textbook, activity 6.2. So the aim of this activity is to observe the phenomenon of total internal reflection and determine the critical angle of the glass. Apparatus needed: semicircular glass block, ray box, power supply and protractor. Material is a white paper. So what we do, we put the semicircular glass block on a white paper, and then we can mark the center of the semicircle or semicircular glass block. Then we draw a normal line, POQ, perpendicular to the boundary. AB is known as the boundary, so between the glass block and the air. And then we can put a ray box at certain angle I, then we can see the angle R for the refracted ray. Now you can observe this video so that you can see clearly what exactly happened. So you can see here we have a semicircular glass block. We already marked on the white paper the angles of incident required. So you can see this is the normal line. Now we put the ray box here so that the light ray will be incident at the required angle of I. So this is angle I equals to 10. So you can see when travel from glass to air, it will be refracted away from normal. So this is angle 20. So you can see as angle I increases, angle R also increases. Now you can see there's the amount of light ray that already reflected here keep increasing. So you can see the light ray here. So when light ray travel along the boundary, here when angle R equals to 90, so you can see large amount of light ray reflect into the glass block. Now you increase greater the angle I, you can see finally there's no more light ray refracted here. All will be traveling in the glass. So we call it a reflected ray. So in this situation, there's no more refraction, there's no more refraction of light, then there's only reflection. So this situation, we call it total internal reflection. Mean all the light will be reflected. Okay, so we can explain further that situation. Let's say when angle I is less than critical angle. What is this critical angle? Or an angle which is smaller. So when light travel from glass to air, it will be refracted away from normal. And then we can see a weak reflected ray in the glass, as you can see before in the experiment carried out. Now we increase the angle until equals to C, where you can see the light ray travel along the boundary. When travel along the boundary, angle R equals to 90. So when angle R equals to 90 degrees, the angle of incidence here, we call it critical angle. So we mark as C. So it's quite easy for you all to determine from that activity. You just make sure the light ray travels along the boundary, then you measure the angle I. So that angle I, we call it critical angle of the glass block. Okay. Okay, let's increase the angle I greater than C. As you know before that, when we increase I, R also increase. When I equals to C, the light ray traveling along the boundary. If you increase the angle I greater than C, of course, it will be refracted further. When refracted further means the light ray now travel back into glass block. So in this situation, we call it total internal reflection, meaning totally reflected ray. Okay, so as you can see here, from here we can conclude there are two conditions for total internal reflection to occur. First, light must travel from denser to less dense. Okay, this one, denser to less dense. And then the angle I must be greater than critical angle of the medium or glass block. So here we can summarize this activity carried out before. So condition to be satisfied for total internal reflection to take place are, so you can see light travel from denser medium to rarer medium or less dense medium. So when angle I is greater than critical angle, it will be reflected. When it reflected, of course, it will all be law of reflection. So you can see angle I equals to R. So first, you must be able to list down the two conditions for total internal reflection to occur. First, light travels from medium of high density to medium of low density. And then the angle I must be greater than the critical angle of the medium. So critical angle C actually defined as angle of incidence when angle of refraction is equals to 90 degrees. Okay. So activity 6.3. This one to discuss relationship between critical angle and refractive index. As we know that different density of medium will have different refractive index. The denser the medium, the higher the refractive index. Now we want to relate between critical angle and refractive index or the density of medium. Inference. Critical angle of the medium depends on the density of medium. Hypothesis. The higher the refractive index, the smaller the critical angle of the medium. Now you can look at this situation, this diagram. We have a glass block here. We use a laser pointer to produce a light ray. Let's say light ray travel from glass to air. So light ray travel at angle C, critical angle. So you can see the light ray travels along the boundary where R equals to 90. So now we want to determine what is critical angle of glass. We mark as critical angle of glass, which is we mark as C. Let's say refractive index of glass is N1, refractive index of air is N2. In my previous video, we have discussed about Snell's law. Snell's law for light traveling from glass to air is given as, or glass to water, or glass to any other medium, we can put as N1 sine theta 1 equals to N2 sine theta 2. Now I refer to this diagram. So value of theta 1 is critical angle. N1 is the refractive index of glass. So you can see N1 sine theta 1. If you put N1 is for refractive index of glass, meaning theta 1 is angle in glass. Theta 1 is angle in glass. And then N2 is air. So N2 is refractive index of air. And sine theta 2. So theta 2 is angle in air. Okay, so we just substitute all the values. So theta 1 equals to C. Theta 2 equals to 90. N2 equals to 1. So by substituting all the values, so you can get this one. N1 sine C equals to 1 sine 90. So you get N equals to sine 90 divided by sine C. Thus we get N equals to sine C. Okay. So generally, this formula can be used to determine critical angle of the medium based on the refractive index given. So we can define N as refractive index of medium, in this case is glass. C is critical angle of glass, in this case is the angle of medium, in this case is glass. Okay, so we have this formula, N equals to 1 over sine C. That's the new formula that we can relate between the refractive index and critical angle. Okay, look at this activity. This activity is to observe phenomenon of total internal reflection in water stream. Apparatus we need is 1.5 liter plastic bottle, plastic basin, laser pointer, wooden block, retort stand, material, water and cellophane tape. You can see initially we put or we cover the hole that already made here. So there's a hole here so that the water can come out. Okay, this is a laser pointer. Okay, what we do, once the water is released out, you can on the laser pointer. So you can see a laser beam which enters the water stream, experiences repeated total internal reflection until it comes out from the end of the water stream. So if water stream replaced by an oil stream, light beam will experience total internal reflection even more times. This is because refractive index of oil is greater than refractive index of water. Critical angle of oil is smaller than critical angle of water. So just now we have discussed N equals to 1 over sine C. So meaning the higher the refractive index, the smaller the critical angle. Once critical angle is smaller, so total internal reflection will be easily occur. Okay, now you can refer to this video so that you can see how this activity is carried out. This one is the bottle. There's a hole here. The lid of the bottle is closed, so the water cannot come out. And there's a laser pointer pointing directly to the hole where the water will coming out. So you can observe what happened when the lid is open. So a stream of water with the color, okay, coming out. Okay, so it's very beautiful color, a stream of water that coming out due to the total internal reflection of water. So water coming out keep experience total internal reflection until reach here. Okay, so you can try this in the lab. So it's very beautiful. I think we can use a very powerful laser pen. Then only we can see the color clearly, and must be carried out in a dark room. Okay. So this activity shows that water which has a certain critical angle will cause this situation. So once the laser pointer point the incident ray to the light ray experience a total internal reflection, thus coming out as a stream of water with a beautiful color. So I think for this part, I will stop here. So you can search more in the internet to view more videos on this activity so that you will understand better. So for this topic, let's summarize what is total internal reflection. So total internal reflection is a phenomena that occurs when light travels from denser to less dense medium, and the angle of incident is greater than the critical angle. Okay. I will discuss about natural phenomena, the application, and some of the problem-solving question. So look at the natural phenomena that occur around us. For example, formation of rainbow. So formation of rainbow is a phenomenon caused by refraction, dispersion, and total internal reflection when light passes through water droplets in the air. So you can see how the light ray from the sun, which is white light, then reach here. When reach here, the light experiences refraction and dispersion. So it will be refracted to a different angle, because different angle for different colors of light, it will refract to different angle. So light ray is white light. It consists of 7 colors. Okay, red, orange, green, blue, indigo, and violet. Okay, so then when reached to all these different colors experiences total internal reflection on the surface of water droplets. Here you can see total internal reflection. And then when reached here, 3, light rays reflected experience refraction and dispersion again when moving from water to air. So here is the total internal reflection. And when reach part 3 again, it will experience refraction. So different color refract to different angle. So you can see now the color will be spread out into 7 colors. So that's how you can see the beautiful rainbow that form due to the phenomenon of refraction, dispersion, and total internal reflection. Second is mirage. Okay. On a hot day and bright day, a car driver sees a blurry image of puddle of water on the surface of the road ahead. So when you are in the car, sometimes you can see something like there's a water on the road, but when you reach that point, there's nothing there. It's like an optic illusion. So what caused this situation? So when he gets nearer to the puddle of water, he discovers that the puddle does not actually exist. So this natural phenomenon is known as mirage, which is caused by refraction and total internal reflection. So you can look at this diagram, especially during hot day. So during hot day, the road is hotter than the layers of air above. Okay, So you can hear the air will be divided to a few layers of air. The above one will be denser, which is cold, and when go to the bottom, close to the root, it become hotter, so it become less dense. So what happened here? Layers of air above the root have different optical densities. So the layer of air just above the root surface is hotter than upper layer. So the layer of hot air is smaller density than the cold air. So you can see a different density of layers of air. So when light travel from different density of air, of course, it will experience refraction. So you can see light from the cloud here. It travel from denser to less dense, so you can draw a normal line here. And then the light ray refract away from normal. Again, when we reach this boundary, it experience again the refraction, refract away from normal. Okay, so you can see when refract away, until the angle I become greater than the critical angle. When the angle I greater than critical angle, what happened to the light ray? It will experience total internal reflection here. When total internal reflection, it will travel back up, okay, to the same medium. So you can see the number 3 here. So number 3 here means the light ray already experienced total internal reflections. So when the light ray gets into the observer's eye, our line of vision is always straight line. So we observe an image form on the road along our line of vision. So because of the light ray coming from the moving object like cloud here, so it gave the effect like there's a water on the road. Okay, so this phenomena we call it mirage or mirage that occur due to the phenomena of refraction here and total internal reflection. Okay. Application, so we can discuss about the prism periscope. We can have a mirror periscope. For the mirror, if we use mirror, it just occur reflection. For mirror, it will absorb quite large amount of the light energy, thus it will produce a very blurred image. There's advantage of using prism because prism will produce total internal reflection. So total internal reflection means we can say nearly total of the light ray will be reflected. So intensity of light will cause the brighter image to form. So prism periscope is used to what? To observe an object behind an obstacle or barrier. It's made up of two right-angle prism, 45 degrees prism, fitted at both ends of long tube. Okay, so light rays from the object travel along the normal to the side AB of the upper prism. The light ray reach side AC without refraction. So you can see light travel in a straight line here. Okay, because it incident along the normal line. I equals to 0, R also 0. That's why it becomes straight here, no refraction. So when reach here, you can draw a normal line here. Okay, so angle I here is greater than the critical angle of glass prism. Normally glass prism is about 42 degrees, the critical angle. So angle I equals to 45 will be greater than critical angle. Same thing here. So meaning all the light ray which is incident along the normal line, it will be reflected because I is more than critical angle. Okay, so total internal reflection occur here and here. There's a light ray that reflected. We go to the next prism. The same thing happen here. You can draw a normal line. Angle I equals to 45. Here also angle I equals to 45 means greater than critical angle, thus totally reflected. Okay, so when gets into the observer's eye, the observer will observe the image which is virtual, upright, and same size. Okay, so you can see a brighter image will be formed when we use glass prism due to total internal reflection. Okay, this is optical fiber. Optical fiber is made of two layers, inner core and outer cladding. The inner core is denser than the outer cladding. Okay, it can be made from pure glass or flat plastic fibers. So inner core, high refractive index or denser, surrounded by layer of cladding with low refractive index or less dense. So light signal enter one end of the optic fiber and experience total internal reflection continuously in the inner core until they reach the other end. As such, signal can be sent rapidly without disturbances from electric signal. So you can see here the light ray gets into the inner core, and then angle here I is greater than the critical angle, total internal reflection, again total internal reflection. So there's a continuous total internal reflection occur. Okay, so the uses of this optical fiber can be used in the medical side. For example, doctors use endoscope to examine internal organs by using optical fibers. Engineers use fiber optic to examine the interior of complex machines. Communication experts use fiber optics for sending data speedily. So this one, when we talk about total internal reflection for telecommunication, so there is no loss of signal. So the image form will be brighter, or the signal received will be maximum. Okay, that's the advantage of optical fiber. So this one is cat's eye reflector. Cat's eye reflector. So you can see on the road, especially the area with less accommodation, normally there's no street lamp. So as a safety, normally there's a cat's eye on the road. You can see on the road there. So during night time, due to reflection, the driver can see the road clearly. So this one is for safety. Okay, because not all area will have these street lamps because of less accommodation. Okay, so cat's eye reflector used for purpose of safety of road users at night. Light rays from car headlights enters the reflector and experience total internal reflection on the back surface of the reflector. So meaning the light coming from the car, when hit the reflector, it bounces back and returns to the driver. So the driver can see something on the road, so can see the track, okay, of the road easily at night. Okay, let's discuss about some of the problems involving total internal reflection. So example 1, figure 6.25 shows light ray traveling from air to prism with refractive index of 1.49. Okay, this is a 45 degrees prism. Calculate critical angle of prism. Complete the path of light ray until it exits the prism. Okay, so to relate between the refractive index given and critical angle, we have this formula. N equals to 1 over sine C, or sine C equals to 1 over N. So you just substitute the value of N here, and then use calculator to find the value of C angle, so we get 42.2 degrees. So critical angle of prism is 42.2 degrees. So P, we want to complete the ray diagram. So ray diagram, this one, for this one, this part. Okay, so you can see, you can draw a normal line here. So you can see angle I equals to 0, meaning R0, no refraction. So you can see it travel in a straight line. Okay, so when hit this surface, you just can calculate what is angle I. So angle I here is 45 degrees. So angle I 45 degrees is greater than critical angle, which is only 42.2. So total internal reflection occur here. So you draw. I equals to R. I 45 meaning R also 45. So we reach this point again. So again I equals to R. I equals to 45. So when I equals to 45 greater than critical angle, again total internal reflection. And come out here also straight line because along the normal line. So this is the ray diagram to light ray, path of light ray for this situation given. Okay, second example, figure 6.27 shows path of light ray traveling through optical fiber from A to B. A, explain the change in direction of light ray at points Q, R, S, T, U. So at point Q, here, refracted light bends towards normal because from air to glass, this is not yet total internal reflection, so refract towards normal. At point RST, total internal reflection occur. At point U, coming out from the glass to air, so refract away from normal. Okay. B, if the refractive index of the optical fiber is 1.51, determine the value of angle X. Okay, this is angle of refraction. So we can use the formula N1 sine theta 1 equals to N2 sine theta 2. Okay, so let's say N1 is air, N2 is glass, the inner core. So N1 equals to 1, sine theta 1 is 45. Theta 1 is 45 degrees. And then N2, the refractive index is 1.51 sine X. So you can find sine X equals to 0.468. Thus you get X 27.9 degrees. C, why must material optical fibers be of high optical purity? High purity material allows the critical angle along the fiber optic to be consistent. All signals which enter the fiber will experience total internal reflection. So that we have a constant value of critical angle, because for high purity, of course, it will have a one density, which is always constant at all points. Okay, let's discuss about formative practice 6.2. You can try first this practice, then you can check the answer. Okay, number 1, figure 0.628 shows the path of light which travel from air to prism. So determine angle of refraction of light ray in the prism. Refractive index of prism is 1.5. Will the light ray experience total internal reflection at the side AB of the prism? Will explain your answer. Okay, A, we want to determine refractive index, determine the angle of refraction. Angle of refraction here. So we can use the formula from the Snell's law. Refractive index of the glass prism is 1.8 equals to sine in air 45 divided by sine R. Here is sine R. So we get the angle of refraction equals to 23 degrees. So here is 23. Okay. B, will the light ray experience total internal reflection at side AB? We need to check the critical angle of the prism. So you calculate the critical angle of prism using the formula N equals 1 over sine C. So from here I get C equals to 33.7 degrees. Now you calculate for angle theta. We want to make sure, does this light ray will experience total internal reflection or refract out here? So we calculate for angle theta, this angle. Okay, just now we have discussed angle of refraction here is 23. Total angle here is 90, meaning here is 67. Okay, so here is 67. This angle is 45. Okay, 45, 67. Thus we get this angle is 60. Okay, so we get here is 60, because you can just total up 45, 67. Sorry, angle here is about 68. It's just wrongly typed here. So here is 68, meaning this angle is 22. Okay, this angle is 22. Okay, so you can just calculate again for this one. So it should be, I cannot get 30, but the value is lower. 90 minus this angle, So we get the value is smaller than critical angle. So when that value is smaller than critical angle, meaning angle of refraction does not exceed critical angle of prism, thus total internal reflection does not occur. Okay, so no total internal reflection, meaning the light ray when reach this point, it will be refracted away from normal. Okay, number 2, Figure 6.29 shows fine optical fiber made up of inner core, which has a high refractive index surrounded by cladding material of low refractive index. So inner core and outer core. Determine critical angle of optical fiber. What is advantage of fine optical fiber? So use the Snell's law, n2 over n1 equals to sine theta 1 divided by sine theta 2. So if we find sine C equals to 0.7778, then C we get 51.06 degrees. Okay. So fine optical fiber able to insert to small parts and easily bend to reach all area. That's the advantage of fine optical